4 billion years, a miracle of an unfolding on a small, sapphire blue marble drifting through the void. From a first rhythmic pulse of a single cell to the complex symphonies of consciousness we experience today, life has been the Earth's most defining feature. But as we look at the timeline of our world, a troubling, beautiful mystery emerges. We have always assumed that Earth is a cradle of life, the unique laboratory where the spark of existence first flickered into being. But what if our planet wasn't the birthplace, but merely a fertile garden? What if the seeds of everything we are were sown in a much stranger, much older universe? Imagine a cosmos where life isn't a rare accident, but fundamental property of matter, waiting for the briefest moment of warmth to explode into bloom. Today, we bridge the gap between speculative physics and biological history to ask, did we arrive here as finished travelers rather than locals? The first few 100 million years of Earth's history were a nightmare. We call it the Hadean Eon, a period of molten seas and a constant, violent bombardment from the heavens. Logic suggests that such a chaotic environment would be the last place life could ever begin. Yet, the geological record tells a shocking story. Almost the very instant the Earth cooled enough for liquid water to pool into oceans, life appeared. It didn't just appear, it saturated the planet. Microbes moved into every hydrothermal vent and volcanic crevice with an intensity that seems almost impossible. This is the life paradox. If life is a result of a 1,000,000,000,000 chemical fluke, why did it happen so quickly on a planet that was still cooling from its own creation? It feels less like a slow, painstaking invention and more like a pre-existing force that was simply waiting for the doors to open.
To understand why this speed is so baffling, we have to look at the sheer complexity of a simple microbe. Even the humblest bacterium is a masterpiece of biological engineering. It must eat, expel waste, and most importantly, replicate. This requires a genome, a massive library of instructions written in the language of DNA. Here lies the ultimate chicken and egg riddle of biology. To build a functioning genome, you need specialized proteins to manage the data. But to build those proteins, you need the instructions already written in the genome. Both are incredibly long, intricate molecules that are statistically impossible to assemble by random chance in a prebiotic soup. If you threw the parts of a watch into a box and shook it, how many billions of years would you have to wait before it told you the time? Earth may not have had enough time to shake the box. If we treat the history of life like a book, we can see that the story gets more complex at a remarkably steady rate. Think of it as an evolutionary clock. By analyzing the functional genomes of various species, researchers have noticed something startling. Genomic complexity appears to double at a constant interval, roughly every 350 million years. From the simple worms of the Cambrian to the intricate neural networks of modern primates, the software of life has been expanding exponentially. This provides us with a mathematical yardstick. If we know how fast the clock is ticking today, and we know how complex life was when it first appeared on Earth, we can follow the curve backward. We can trace the lineage of the genome back to its hypothetical page 1, the moment the very first letter of the code was written.
When we perform this calculation, the result is staggering. If the exponential growth of life's complexity has been constant, the origin of life doesn't land 4 billion years ago on Earth. It lands 10 billion years ago in deep space. This is more than twice the age of our entire solar system. If this biological Moore's law holds true, it resolves the life paradox instantly. Life on Earth appeared so quickly and in such a sophisticated state because it had already been evolving for 5 billion years before the Earth even existed. We aren't the primary authors of our story. We are a sequel. This suggests that the cosmos is not a graveyard occasionally interrupted by a spark of life, but a vast, ancient ecosystem where the seeds of biology drip between the stars, hibernating in the cold, waiting for a warm, wet rock to call home. But could life really have existed 10 billion years ago? The universe back then was a much stranger place. Shortly after the Big Bang, the cosmos was a searing furnace, but as space expanded, it cooled. Scientists have identified a fascinating Goldilocks period in the very early universe, roughly 10 to 17 million years after the beginning of time. During this era, the cosmic microwave background radiation, the heat left over from the Big Bang, would have kept the entire universe between 0 and 100 degrees Celsius. For several million years, every single corner of the cosmos was at a temperature that could support liquid water. In this baby universe, the vacuum of space wasn't a freezing death trap. It was a warm, habitable medium. It was a brief moment where the entire universe, from end to end, was essentially one giant cradle for life.
Of course, temperature isn't everything. You need the building blocks, carbon, oxygen, nitrogen, the heavy elements forged in the hearts of stars. Standard cosmology suggests these weren't common so early on. However, in the ultra-dense regions of the young universe, the very first stars were massive giants that lived fast and died hard. These primordial stars would have gone supernova in just a few million years, seeding the warm, baby universe with the ingredients for chemistry. In these dense, early nurseries, planets and asteroids could have formed much sooner than we once thought. Imagine a universe where the first oceans weren't trapped on planets, but existed as massive clouds of water vapor and droplets, warmed by the Big Bang itself, and fertilized by the dust of the first dying stars. We must also consider that our definition of habitable is deeply biased by our own experience. We look for water, but perhaps the first ancestors of life were far more exotic. In the early universe, substances like ammonia or ethane could have remained liquid at temperatures much lower than water's freezing point. These alternative solvents could have extended the universe's habitable window for tens of millions of years longer. In this scenario, life didn't need a sun or a stable orbit. It could have thrived on any rock, in any nebula, or on any rogue moon drifting through the cosmic haze. The prebiotic soup wasn't a small pond on a single planet. It was the universe itself. We are talking about a period of several dozen million years where the conditions for life were effectively universal.
As the universe continued to expand, the lingering warmth of the Big Bang eventually faded, and the cosmos grew cold and dark. But by then, the seeds had already been cast. Life is incredibly resilient. We know that certain microbes can survive the vacuum of space, extreme radiation, and billions of years of deep freeze in a state of suspended animation. These ancestral forms have been preserved within the icy hearts of comets or the rocky shells of asteroids, cosmic escape pods carrying the genetic blueprint of the early universe. For billions of years, this great diaspora drifted through the void. They were silent travelers, waiting for the gravity of a young star system like ours to pull them in, providing the heat and water necessary to wake up and resume their 10-billion-year-old journey of evolution. This theory, while speculative, changes everything. If life is 10 billion years old, then it should be everywhere. We might find the frozen fossils of our cousins in the dry riverbeds of Mars, or swimming in the dark, warm oceans beneath the ice of Europa. If we find life on Saturn's moon Titan, life that uses ethane instead of water, it would be the smoking gun for a baby universe that could have birthed many different biological lineages. We look at the stars and wonder if we are alone, but the truth might be that we are part of a vast, interconnected cosmic family tree, sharing a common origin that predates the very ground we stand on. We are not a lonely accident of chemistry. We are the latest bloom in a garden that has been growing since the dawn of time. The universe is calling us to find our siblings. Let's go and look for them.